Welcome back. In our previous video, we looked at how we could consider trigonometric expansions, particularly for the cosine and sine functions, by using the de Moivre's theorem. This time around, we have an example where we are to expand cos 5 theta. As always, make sure to like, share, and subscribe, and turn on your notifications so that you do not miss any of our videos. So, let's begin. Now, for cos 5 theta, remember that in nominal real analysis, you could expand cos 5 theta trigonometrically by using what we call the addition of factor formulas and then breaking it down from there. However, using the de Moivre's theorem, you do not need to go that route, and you could simply expand it by using the relationship between the cosine and the real part of the power multiple of the function of z. How exactly do we mean? Remember that we can write cos 5 theta as the real part of cos theta plus I sine theta raised to the power of 5. If you are wondering why we are able to write it in this regard, take a minute, pause this video and look at our previous video on how we derived these equations for more clarity. Now that we have this, the only thing that is left is for us to take this representation and expand this as much as we can. This would mean that cos 5 theta would simply be the real part of the expansion of cos theta plus I sine theta. Now, in this regard, the expansion will simply be by binomial expansion. We would have cos raised to the power of 5 theta plus 5 cos raised to the power of 4 theta I sine theta plus 10 cos cube theta I sine theta all squared plus 10 cos squared theta I sine theta all cube plus 5 cos theta I sine theta raised to the power of 4, then plus I sine theta all raised to the power of 5. This is going to be the full expansion. Now, if you are wondering how we were able to easily find these coefficients 1, 5, 10, 10, 5, 1, it comes from us applying directly the Pascal's triangle for binomial expansions. Remember that the Pascal's triangle gives you the nominal coefficient of expansions based off the expansion of x plus 1 raised to the power of n. And then that expansion can then be reformulated based off whatever is inside your bracket. Remember that expansion, as it's colloquially known, if we were to write it here, you have x plus 1 raised to the power of 0, you would say the coefficient is simply 1, because any non-zero value raised to the power of 0 gives you 1. However, when you have x plus 1 raised to the power of 1, then the coefficients become 1 and 1, because you have exactly the same thing. So the coefficient of x is 1, and then the constant is 1. From there on, Pascal tells us that for the rest of the coefficients, the leading coefficient and the last coefficient is always 1. And then whatever is inside is the successive addition of the coefficients before it. So 1 plus 1 gives us 2. Hence, we have these 2. When we go to x plus 1, when we go to x plus 1 raised to the power of 3, this time around we would have the first and the last remains 1, then 1 plus 2 gives us 3, 2 plus 1 gives us 3, such that when we go to x plus 1 raised to the power of 4, you would have the first and the last remaining 1, and then 1 plus 3 gives us 4, 3 plus 3 gives us 6, 3 plus 1 gives us 4. Hence, you have 5 coefficients. And then when we go to x plus 1 raised to the power of 5, you would have the first and the final being 1. 1 plus 4 gives us 5. 4 plus 6 gives us 10. 6 plus 4 gives us 10. And then 4 plus 1 gives us 5. Hence, 1, 5, 10, 10, 5, 1. 1, 5, 10, 10, 5, 1. So we have applied this Pascal's triangle to easily carry out our expansion without us needing to say we are applying the combination formula, for instance, towards expanding it, or to apply the differential method for binomial expansion. All of this can be simply done using the Pascal's triangle. I digress. Now that we have this, the next thing for us to do is to evaluate and open this bracket so that we'll be able to know which parts are the real parts and which parts are the imaginary parts. Now, when we open this bracket, we would have, of course, cos raised to the power of 5, theta remains. Then this would be plus 5i cos raised to the power of 4 theta sine theta. That remains as well. And then here we see I squared gives us minus 1. So we have minus 10 cos cube theta sine squared theta. And then I cube gives us minus I. So we have minus 10i cos squared theta sine cube theta. And then I raised to the power 4 gives us 1. So that means in this regard, we're going to have plus 5 cos theta sine raised to the power of 4 theta. And then I raised to the power 5 gives us I. So that gives us plus I sine raised to the power 5 theta. So what do we notice immediately? We notice that after this expansion has been completed, the only parameters without an I value is simply 1, 2, and 3. The other three have the I value. So the ones without the I value are the real parts of the expansion. So it means that we can say that cos 5 theta is in fact equal to cos raised to the power of 5 theta minus 10 cos cube theta sine squared theta plus 5 cos theta sine raised to the power of 4 theta. And this is very, very, very correct. Now that we have this, of course, we can decide to now say the expansions or the representation of the sign, we want to reduce them or rewrite them in terms of the cosine by using trig identity. Since we know that sine squared theta equals 1 minus cos squared theta, then it would mean immediately that cos raised to the power of 5 theta can be written as cos 5 theta minus 10 cos cube theta into 1 minus cos squared theta plus 5 cos theta into 1 minus cos squared theta all squared, because of course sine raised to the power of 4 theta is in fact sine squared theta all squared, which is in fact 1 minus cos squared theta all squared. So that the expansion of this would be cos raised to the power of 5 theta minus 10 cos cube theta plus 10 cos raised to the power of 5 theta, of course, where we expand this, plus 5 cos theta into the expansion of this function, 1 minus 2 cos squared theta plus cos raised to the power of 4 theta. Now that we have this, the next thing that needs to happen is for us to expand the last bracket that we have. It then follows that cos raised to the power of 5 theta will now simply be equal to cos raised to the power of 5 theta. Let's have all our times out first before we begin to add and subtract where necessary. Minus 10 cos cube theta, right? Plus 10 cos raised to the power of 5 theta. Then plus 5 cos theta minus 10 cos cube theta. Then plus 5 cos raised to the power of 5 theta. So if we bring this all together, we notice immediately that we would have 16 cos raised to the power of 5 theta minus 20 cos cube theta plus 5 cos theta, and this would be our final expansion for cos 5 theta. So you can try as much as possible to do same using your additional factor formula and see if you get the same answer. Also, as a practice, try as much as possible to use this method to expand sine 5 theta. Do not forget, as a hint, that sine 5 theta is simply the imaginary part of cos theta plus I sine theta all raised to the power of 5. Remember that for this, we have already done you a great favor of carrying out the expansion to this point, such that instead of extracting the real part, in your own case, you'll be extracting the imaginary part in order to get sine 5 theta. I hope to hear more from you about what you got as your answer for sine 5 theta in the comments. As always, make sure to like, share, and subscribe, and turn on your notifications to make sure you do not miss any of our videos.